So yes, there's a lot to do with these problems. We'll start off, and I'm going to go through it one bit at a time, even though I know I gave it all to you. Okay, so you know about increasing function and decreasing functions from pre-calc, but you don't know how to associate them with derivatives. All right, and so this is where the stuff is kind of new. But the concept of increasing, decreasing is not. Okay, when the first derivative is positive, that's what this is saying, on some interval, then the function is increasing on that interval. And if we think about what the first derivative is the slope of the tangent line. So increasing, meaning that the graph is going up from left to right. Okay? And then, of course, if the derivative is negative, then it's decreasing because the slopes are negative as we go from left to right. And then we kind of put it together. We have what's called the first derivative test. And this is where you're going to use number lines. And so what we're looking for is a change in the first derivative sign. So first off, it has to be continuous, and we look at the critical numbers. So if the first derivative changes from positive to negative at c, whatever that value is, it will have a local maximum. Okay? Now remember that an absolute maximum can be at an endpoint. So when we talk about things like this, we're only talking about local maxes. Okay? And then if it changes, so positive, so think of, in my mind, I'll tell you how I think about this every time. When I think about positive to negative, I envision a parabola in my head, even though we're not necessarily talking about parabolas. But at a place where we have a critical number, which means there's a horizontal tangent, you're going to have at least something looking like this. Okay? So positive to negative, that's where I'm going to have a local max. So, and I'm just telling you because sometimes it's tricky. I still have to think through it. I'm like, positive, and you might even see me sitting over there doing like a hand gesture going, okay, positive, then negative. All right, maximum, got it. So if that helps you do it. If it changes from negative to positive, then it has a local minimum at C, or relative minimum, okay? And then, and I know you have all this. Sometimes it can be positive to the left and to the right of that value, or negative, so there's no sign change, which means there will not be a local min or max. That's the important piece here. There has to be a sign change. And when we say sign change, we're saying either from positive to negative or negative to positive. I would not use the idea, because I see this happen, and this is where I get a little worried. I would not say, oh, there's no sign change, okay? Or there's a sign change from here, that's why it's... I would be specific and talk about the first derivative goes from positive to negative. And you can put a plus symbol and a minus symbol. You don't have to write the word positive and negative. But that is a good explanation, demonstrating that there's a sign change. And then you can talk about maximum mins from there. Okay. If there is no sign change, what you'd want to say is it's positive on both sides, so therefore there's no max or min or negative on both sides, something like that. Okay. So that's the first part. Now, you've learned a little bit about concavity in pre-calc. But today we're going to talk about it in a different way than what you're used to. Did you talk about tangent lines for concavity? Or did you just think about that it opens up, opens down? You did. Okay, good. All right. So if the graph is above the tangent lines, if the tangent lines are below the graph, it is concave up. If the graph is below the tangent line, or the tangent lines are above the graph, then it's concave down. Okay, so that concept is not different. This concept will be different. Now we're looking at the second derivative. Remember that this means just two derivatives. Okay, so if the second derivative is positive, it will be concave up. If the second derivative is negative, it will be concave down. That's just something you're going to have to know. Okay. And then the last definition that I gave you here Okay, if the concavity changes from concave up to down or down to up, then we have what's called a point of inflection or an inflection point. Most of the time we call it a point of inflection. I know in the book they said inflection point. But oftentimes what you'll see is this abbreviation, which is fine. POI, point of inflection. Okay, there has to be a change in sign for the second derivative in order for there to be a point of inflection. The concavity can only change when the second derivative sign changes. Okay, now when you look at the graph, oftentimes you can see where that happens, but sometimes it's harder to see. Okay, and we're going to do that next. Did you guys learn about points of inflection? Or did you just talked about concave up and concave down? Okay. Okay. So where the concavity changes, that's when we have a point of inflection. Now, I get this. So now we can start doing some stuff. Okay. Here's a graph. And so what I want you to do, okay, is I want you to do these questions, all right? One, on what interval is f of x increasing or decreasing? Okay, so state the increasing ones if there are any, state the decreasing ones if there are any. Okay, and then you have to give an explanation. These are the types of things you would see on an FRQ. Okay, and then number two, at what values of x does f of x have a local min or local max? And explain. Three, what intervals is it concave up or down, and explain, and then same, which are points of inflection. So remember, for a point of inflection, you actually have to state the point. The other ones are just asking you for x values, okay? So give that a shot. Yeah, for this problem, assume that those are endpoints. I would be putting arrowheads on them. So yeah, assume those are actual endpoints and that they don't continue on. So pretty straightforward for number one, increasing. You're looking for where the tangent lines have positive slope. Okay. Should your intervals be open intervals or closed intervals? One of those. Open. They should be open. Because if we take the tangent line at where the increasing, decreasing changes, in other words, where the slope of the tangent line changes, that there's a point where it's zero. Okay. So they should be open. So we have increasing from 1 to 3 right here. Increasing. We have increasing from 5 to 7. And we have increasing from 8 to 9. This is my bad. That should be just f. That should not be f of x. So yes, if you did it based on the fact that it was f prime, that is my mistake. I did not erase that. It should be f of x. That is my fault. So that would change all your answers. How many did it as it was f of x anyway? Okay, good. Sorry about that. All right, then decreasing. Now, at each subsequent slide, that tick mark's going to come back in, and I'm not going to erase it every time. So just know that this is the graph of f of x. Okay? Decreasing, of course, all the ones that are going down, so that because they have positive slopes of the tangent line. Okay, decreasing from 0 to 1, from 3 to 5, from 7 to 8. Eventually, we will look at ones like that. Okay, and again, the tangent lines are negative. Okay, so that one. 0 to 1, we're negative. 3 to 5, we're negative. From 7 to 8, negative. Okay? All right, on what values of x does f of x have a local minimum or maximum? Well, we can see where the minimum are. Right? And how many local minimums do you see? How many local max do you see?
2. How big is 9?
Right. 9 can't be 1 because there's not stuff on both sides. So, yeah. And it said to explain. Okay. So local min at 1, 5, and 8 for x. And it changes from decreasing to increasing. Okay. You could have said the first derivative changes from negative to positive, but we really didn't actually find the first derivative. Okay. And then, of course, we have a local max in 2 places. At 3 and 7, changes from increasing to decreasing. Okay, we good so far on those first 2? All right, what intervals is it concave up? So remember, think about the tangent lines. Okay, so right here, the tangent lines are all below the graph, and then right here it flips, and then it's above the graph. So I'm concave up from 0 to 2, from 4 to 6, from, I don't know what this is, 7.5-ish to 9. And then concave down from 2 to 4, from 6 to 7.5. Oops. And you could say the graph is above the tangent lines. You'd want to say something about the tangent lines. If you said the tangent lines were below the graph, that works too. And then, of course, concave down from 2 to 4 and 6 to 7.5 because the graph is below the tangent lines. Or you could say the tangent lines are above the graph. Either one. Those would be your explanations. So all we have to do is look at what x values have changes in concavity. And then we're going to eyeball and try to figure out where those y values are. Okay? Let's see if, so where's 1 for sure? Where's definitely a point of inflection?
1, -1.
Nope. Okay, so I have one here. I have one here. Do I have one here?
No.
Well, so let's just compare. From 2, then it changes to, so at 2 it goes from concave up to concave down until we get to 4. And then at 4 it goes from concave down to concave up. And then at 6 it goes from concave up to concave down. And then 7.5 it goes from concave down to concave up. So we actually have 1, let's just mark them. I got one here. I got one here. I got one here. I got one there. Okay, so those 4 are my points of inflection. Now, these 3 are pretty easy to find. This one we're guessing because we don't know what the y value is. So the first one is 2, 0 because we go from concave up to concave down. And that's all you have to do for an explanation. Okay, eventually we'll talk about the second derivative, but we're not there yet. Then at 4, 0, we go from concave down to concave up. 6, we go from up to down. All right, what do we want to say? 7.5 what? 2 maybe? I don't know what we'll see. That's what we're guessing. I said 2. There you go. 7.5 to 2 because we go from concave down to concave up. So again, here are my points of inflection there, there, and there. So when you're given the graph, it's pretty straightforward, pretty simple. Eventually we'll talk about when you are given the first derivative graph, how to tell all those things. But we're not there yet, okay? Questions so far? All right, now we get into the problems that ask us to do a lot. Granted, we did a lot here, but now you're gonna use some calculus to do that. Because we didn't really need calculus to do this. We could just kind of eyeball it. That's why you did a lot of the stuff in pre-calculus. So I think you have your directions on the next one, and then I gave you the problems, right? So for each of these functions, we're going to determine the intervals where it's increasing and decreasing. We're going to find the local min or max. We're going to do everything that we just did with the graph, but this time we're going to do it without a graph. Okay, and we're going to use the first derivative test. We're going to use the second derivative test, and we'll get into all that. I guess they haven't called the second derivative test is something different. We're going to do the concavity test. We will get to the second derivative test here in a minute, though. Okay? So here's our problem. Okay, that should be the next thing on your screen, yeah? All right, so to do all of this without a graph, we need the first derivative and we need the second derivative. And so we're going to start with our conditions. Okay? We need to make sure that it's continuous. Because if it's not continuous, then that could create some problems. Is this graph continuous? Does it have any holes or any undefined spots or anything like that? No, it's not. It does not. Okay? So it's always continuous. And that's something you need to state. Okay? So once we've done that, we can find the first derivative. The first derivative of this is pretty easy. Now, you guys are pretty good at this stuff. Okay? And from here, we have to find the critical numbers. Because the critical numbers, if there is going to be a change in sign from negative to positive, positive, negative, in the first derivative, they're going to happen at the critical numbers. So in order to do that, we need to set this thing equal to 0, which is going to require some factoring. Okay, so I'm going to pull the 3 out. That'll make this easier. And then it's just a matter of setting that equal to 0. I'm going to factor this out and then set it equal to 0. Actually, I don't know. I didn't technically ever set it equal to 0, but it's fine. So the factors of -3 that add up to -2 are -3 and 1. And this would be a perfect example where you wouldn't be allowed to use a calculator. Okay. So what are the critical values that come out of this? When does this equal 0? What does x equal? 3 or -1? Those are my, okay, these here are my critical numbers. Now, here's what we do with that. Okay, we're going to make a number line. And on that number line, we're going to include only -1 and 3. That's all we have to do. And I'm going to label it the first derivative because eventually we're going to have a second derivative number line too. Plus, this helps guide us as to where we're plugging values in. Okay? So we're only plugging in to here. And I like to plug into the factored form because I find it easier. Because we're just trying to figure out if this is positive or negative, if this is positive or negative, if this is positive or negative. Now, a lot of the times they will alternate, but not all of the time. So you actually have to check all of those intervals. All right, what's the easiest one to check first? 0. So if I plug 0 in here, this becomes negative, this becomes positive. This 3 is really inconsequential in terms of determining the sign. So a negative times a positive, of course, is a negative. And you don't have to show work for that. You're allowed to do that in your head, okay? But you do need to show that it is negative, okay? Now, we're going to go over here next. All right, so let's say I pick 4. Is this positive or negative? If x is 4. This is positive, which means this area is positive. Okay? Might as well pick -2. -2 minus 3, that's a negative. -2 plus 1, that's a negative. Negative times a negative is positive. All right? So we are now in the position to answer the first part of the question. Actually, the first 2 parts of the question. we can say where it is increasing, where it is decreasing, and where there's mins and maxes. Okay? So let's start with the increasing. Increasing is where the first derivative is positive. Okay? So I have two intervals that I need to write. I'm less than -1, greater than 3. Usually we write them in interval notation. So it's increasing from -infinity to -1 and from 3 to infinity. And that's where we have these positive signs. Okay. Then, of course, it is decreasing in here from -1 to 3. I'm assuming this is all new in terms of looking at it this way, yes? Okay. Now, to determine a local min or local max, I have to keep straight which one is which. Positive to negative, local max. Negative to positive, local min. So I have two places where there are sign changes. I have one here, I have one here. This is going to give me a local max, this is going to give me a local min. Okay. So local min is f of 3, because it happens at 3. So now when I plug this in, I've got to plug it into here, because remember, this is a point on the graph. So this 27 minus 27 minus 27 plus, so that's -20. Okay. Just plugging 3 in. So my local min is at -20. That's the smallest value. It happens. Sorry, the local min is at 3 and it equals -20. So there's not going to be in that area any values less than that. Question?
How do you know it's at 3 again?
Because I go from negative to positive. So again, think about this way: negative slopes to positive slopes. And so I have a local min at the bottom there. Okay. And then, of course, I have a local max because I go from positive to negative right here. So that's f of -1. It's going to occur at -1. I have to plug that in. So this gives me -1 when I plug it in. This gives me a +1. So I've got -1 minus 3, that's -4. Plus 10, because -1 times that, plus 9. I don't know why I said 10. I probably went 9 plus. All right, let's go back. -1 minus 3, that's -4. Plus 9, that's 5. Plus 7 is 12. Okay. So that's where I'm going to have a local max. Okay, so we've done the first two parts. That's all we've done. We've found out where it's increasing and decreasing. We have found out local min and max. What we need to do now is find out about concavity. Well, concavity requires us to take the second derivative. Okay, so I just take this and take the derivative of this. So that's 6x minus 6. Factor the 6 out. So what's going to make this equal 0? 1. So I got to worry about where x equals 1, and I'm going to put that on the number line. So whenever you see a problem like this and they ask you to explain, the number line is often the explanation. That's supporting evidence. Okay? And again, when I plug, let's say I plug 2 in, is this positive or negative? Positive. And then if I plug 0 in, it's negative. Okay, so that side's positive, that side's negative. Okay, so let's talk about what that means. Where it's negative, that means it's concave down. Where it's positive, that means it's concave up. So we have a change in concavity at x equals 1, which means there's also a what? Point of inflection. Okay? So for concave up, the interval for concave up is 1 to infinity, because it is positive. Concave down is negative infinity to 1. Okay, so we have a point of inflection where x equals 1, but when we find the point of inflection, it actually has to be a point. So this is is how I start. And you can write POI, that's okay. Point of inflection, at 1. Where do I plug that 1 in? You have 3 options. The function, the first derivative, the second derivative. The function, because this is a point on the graph. So I plug 1 in. 1 minus 3, negative 2, minus 9, negative 11, plus 7, negative 4. There's my point of inflection. Okay? Questions? All right, got another one. Now, with a problem like this, we have options. If we can avoid using the quotient rule, let's avoid using the quotient rule. Okay. How could I split this thing up?
4x plus 1 times x to the negative 2.
I'm sorry, what did you, at the beginning? What?
Or x to the 4th plus 1 times x to the negative 2.
Oh, I see what you're doing. You're just moving the x minus 2 up. Yeah, but we can even do more than that.
X squared plus 1 over x squared.
Yep. So I could split this up. There. Just put that denominator under both of them. And what that does for us is it gives us 2 separate terms. Okay? And yes, 1 over x squared, but that's the same as x to the negative 2. So I've got x squared here. I've got 1 over x squared, which is x to the negative 2. And the reason that I want that to happen is because we know we're going to have to differentiate it twice. Which, if you have to use the quotient rule twice, that's going to get messy. So avoid it when you can. Okay? Is this always continuous?
0.
What about it?
Negative 1 is 1.
X cannot equal 0. Right? Because if x equaled 0, then the bottom is 0. So we're not always continuous. Doesn't mean we can't do the problem. We can still do the problem. We just have to recognize that there's going to be an asymptote at x equals 0. Okay? And you're about to see what can happen when you have asymptotes. All right, so we take the derivative. This one's easy. Negative 2x to the negative 3. Again, we've been talking about this, so we're going to keep talking about it. What is the lowest power on the variable here? X to the negative 3. So that's got to come out, and the 2 has to come out too. And remember, this is x to the 1, so I'm going to have to do 1 minus negative 3, which is going to give me a 4. Bless you. Now, we could factor this more and go x squared plus 1, x squared minus 1. We could do that. Obviously, x squared plus 1 doesn't give us anything because then somehow x squared has to equal negative 1, which we know is only an imaginary situation. What is x going to equal in order for this whole thing to be 0? 1 and negative 1. Okay? And I also have to pay attention because here, when this is 0, a critical number can be where it's undefined as well. So my x values that we need to look at, because again, these are the critical numbers. The critical numbers include undefined numbers. So that's why the 0's in there. So we have to check, because that's a spot where we could still have a change in increasing versus decreasing. So when you do that, I'm going to show you how to do that. When you draw your number line, it's going to look a little different. Okay, so first off, we start off with our number line like this. -1, 0, and 1. And then the first thing that I'm going to do is I'm going to put that number in there that makes it undefined. And the way that we do that is we just put an open circle right there at 0. Okay, there is no point at 0. When x equals 0, there is not a point there. So we just put a little open circle. And then the testing of the positive and negative is still the same process. Okay? So why don't you go ahead and do your testing and fill the number line. How many pluses and or minuses will we have here? 4. Okay, why don't you fill that out, please? I'd like to start with the easiest one first. Okay? And so because of this term here, I can get negative numbers, right? Because this is really 2 over x to the third, bless you, and then x to the fourth minus 1. That's the way you want to think about that. So I can get negative numbers here, okay? So we have to be careful on this side, but let's start with something easy. If I start up here, okay, and I put some number that's bigger than 1 in for x, and I take it to the fourth power, this whole thing is going to be positive, no matter what number I pick. This number ends up being positive, and then if I take that same number and cube it, it's still going to be positive. I'm going to get a positive times a positive. And so that first section is positive. From 1 to infinity is going to be positive. All right, now when I'm in between 1 and 0, and I saw some of you writing 1/2, which is good. Okay, if I take 1/2 to the fourth power, I get 1/16, which means this whole thing is negative. If I take a positive number to the third power, even if it's in the bottom, it's still positive. So I've got a positive times a negative, which makes this negative. So we'll stick with it here. So if I had -1/2, this is still going to be a negative number because -1/2 to the fourth is positive 1/16, so I still get a negative here. But now if I have -1/2, a really small number down here, to the third, it stays negative. So now I have a negative times a negative. Wait a minute. Yes. So a negative times a negative, of course, is a positive. So if I take a negative number in here and I take it to the third power, it's still negative. I get a really small number, so a negative times a negative is a positive. And then lastly, if I pick a smaller negative, this is going to be positive because -2 to the fourth is a positive, so this is positive. But then this -2 is going to be negative, okay? So this one turns out to go negative, positive again. Again, they won't always. So you got to be careful with that. Those are tricky. And then, so from here, we just have to state, where is it increasing? Well, it's increasing where there's positive values. So from -1 to 0 and from 1 to infinity. It's decreasing where there's negative values. So negative infinity to -1 and from 0 to 1. All right, when we talk about a max or a min, this is where that gap in our graph is going to come into play. Because there is not a max or min at 0. There is not a point at 0. So what we really need to focus on here, because the mistake that kids will make is you'll say there's a max right here. Because you go from positive to negative. There's not a max here. There is literally nothing here. Okay? So in this case, I have a min and I have a min. I do not have a max. Okay? So I have local min at f of -1. Now we're going back to the original problem. And the thing that's nice is the x is raised to a even power. So this is 1, this is 1, regardless of which one of these I plug in. So I get 2 over 1, 2 over 1. So both of those are 2. Now the next part talked about this local max, right? Ideally, it would be here, but there's no point here. You should state that there isn't one. You should not just leave that off. Because if you leave that off, a reader might think you just forgot to do it. It is important to state that there is not one there. Okay? Does that make sense? Do you have questions about why there isn't one there? Yes?
Yes.
What is your question? Why isn't there one there? There's literally no point there because when x equals 0, we are undefined. So that's why we put that open circle there.
Didn't we do one, like, in one of the first chapters that approaches a certain?
Yeah, that's when we get to limits. That's a different thing. Yeah. I mean, if we were asking for the limit at 0, we could find what that was. That does, well, actually, it goes, I don't think it exists because one goes positive, one goes negative. So I don't think that limit at 0 exists. All right, let's keep moving. So to find concavity, I got to find the second derivative. So I take the derivative of the derivative. So this is going to be 2 plus 6x to the negative 4. Okay, the derivative of the derivative. So here's what's interesting about this, okay? This never equals 0 because I have an x in the bottom. So I only have one critical number. X equals 0 is a critical number. It's not a 0, it's a critical number because it's undefined there. So it's a critical number. So why is finding a critical number important? Well, because we still have to test the concavity on either side of it. So when I come up with that number line, it's going to look very similar. I have that open circle again at 0. Okay, so go ahead and test either side of that, please. Now, when we look on either side, again, remember what we're thinking about. We're thinking about this as 2 plus 6 over x to the 4th. Can this thing ever be negative? No, because I'm raising something to the 4th power, which means it's positive on both sides. Okay? So it's always concave up. However, because it's discontinuous, okay, we can't say that it's concave up from negative infinity to positive infinity. You can't say that because there's a gap. There's a gap at 0. So when we talk about concave up, we have to make a distinction. Okay? It's from negative infinity to 0 and from 0 to infinity. And for those of you who are wondering, like, isn't that just saying all real numbers? Negative infinity to infinity? No, it's not. 0 is not included in either of these, right? Because these are open intervals. So when we say that, we have to distinguish it. And that's what happens with a problem like that, okay? So then is there a point of inflection? Does concavity ever change? No, it doesn't change. There's no points of inflection. Okay. This thing is, for wherever the graph is, it is always concave up. Yeah. All right, we've got a couple more things to look at. Oh yeah, we do. So now we need to talk about the second derivative test. Okay, this is in your notes. And here's where it flips on you a little bit. The second derivative test is a test to determine whether or not there's a local min or max. All right. Sometimes, based off the information they're going to give you, you don't have enough information about the first derivative to find a local min or max. But we can use the second derivative test to do that. They can only occur when there are critical numbers for the first derivative. So where the first derivative equals 0. If the second derivative is positive, okay, then there's a local min. Well, because if the second derivative is positive, that means it's concave up. So it will have a local min. If the second derivative is negative, then it's concave down, has a local max. Okay, that is the second derivative test. So I have a question. Use the second derivative test to determine any local mins or max. So you have to, first off, you have to show that you have a critical number at the first derivative. Then, if at that number we have a positive second derivative, then we have a local min because it's concave up. If at that number, the second derivative is negative, meaning it's concave down, then we have a local max. Okay, so we just take the first derivative. We got to find the critical numbers of that. And this is continuous everywhere. All right. So x can be 0, x can be 2, I think. No, 4, sorry. Okay, take the 3x out. Yeah. So those are the places that we're gonna check. We're gonna check the second derivative at 0, and we're gonna check the second derivative at 4. And we'll decide the sign of the second derivative, and then we'll know whether or not we have a local max or min. So the second derivative is 6x minus 12. And I don't need to, I mean, you can factor, but you don't need to. But what we need to do is test f of f double prime of 0 and f double prime of 4 and see if we get a positive or a negative, okay? So when I do this, when I plug 0 in, what do I get? Negative 12, okay? And then when I plug 4 in, 24 minus, I have positive 12, okay? So here's what this means. Because the second derivative at 0 is negative, that means it's concave down, so it has a local max. Second derivative at 4 is positive, which means it's concave up, which means we have a local min. Now, in order to do this, it's just a matter of plugging those numbers in where? Into the original. Okay, so I'm going to find f of 0 and f of 4. Those go into the original. The 0, 1 is super easy, right? That, when I plug 0 in here, that goes away, it's just 10. Okay. When I plug 4 in, that's a little trickier, right? 4 to the third, that's 64. 24 times 6, or sorry, 6 times 16, I don't know where I got 24 from. 4 squared is 16. 16 times 6 is 96. So I have 64 minus 96. Negative 32. Less than negative 22. Okay. So that's my local min and local max. Again, whenever we're finding those values, we plug them into the original. Questions? We have one more thing to do. And this is the trickiest thing. Save the best for last. Yes. All right. So this one is tricky, okay? And problems like this can be tricky, but you will be expected to do them. There's a lot of information here, okay? A lot of information here. You will have a problem like this on your upcoming quiz, okay? So pay close attention. They tell us some values of first derivatives at certain, they tell us that the first derivative at 1 and negative 1 equals 0, okay? They tell us that the first derivative is negative for certain intervals and positive for certain intervals. They tell us the second derivative is negative for certain intervals and positive for certain intervals. Okay? And so, notice how it says sketch a graph. Because it is possible to have different answers that are still both correct. They all have to have the same characteristics, even with multiple graphs that would work. And I'm going to show you, I think, 3 of them that will work for this, okay? Now let's break down each one of these lines and tell you what that means, okay? When I have a slope that equals 0, when I have a first derivative that equals 0, what's going on here? What are they telling us? What information are we getting from this orange line? There's a horizontal tangent at 1 and negative 1. That's what they are telling us. You have horizontal tangents there, which means we have mins or maxes there, local mins or local maxes there, okay? That's important. Because remember, if it's a local min, it's going to look sort of like a upward-facing parabola. If it's a local max, it's going to look like a downward-facing parabola, okay? This next line is telling us, since the first derivative is negative, what is this really saying? The absolute value of x is less than 1. What is x between? X is between negative 1 and 1. That's what that's really saying. Okay? It's between negative 1 and 1. This is a compound inequality. Absolute value inequality means you have x since it's less than, remember that? And flip it and change it. This is what this is saying here. Anytime you have an absolute value which is less than, that's that old thing we did in chapter 2 in algebra 2. Less than to compound inequality. It's a disguised compound inequality. So in between negative 1 and 1, we know that this graph is decreasing. Okay, so that's what that's telling us. It's decreasing. And then here, it's telling us greater than 1 and less than 1, it is increasing. What is this line telling us? What is this line telling us about? If the second derivative is negative, what is true? It is concave down. It is concave down. And then this one is telling us that it's concave up. All that information, okay? That's what you get from all of that. And what you have to do is mush it all together and make a graph out of it that has all of these characteristics, okay? So let me break down the best way to do that. And if drawing a number line is going to help you see it, then that's what I recommend that you do, okay? So for the first derivative, they tell us we have zeros at 1 and negative 1, which means these two numbers are my critical numbers. And so when I set up a number line, I set it up using negative 1 and 1. And now they give us the positive negative, right? So in here, they tell us it's negative, and outside, it's positive. Okay, so that's what our number line looks like for the first derivative. Okay, and as we discussed earlier, this means here I have a local min, and I have, a local max and a local min. So here's my local max, here's my local min. Again, because when the sign of the first derivative goes from positive to negative or from increasing to decreasing, we have that local max. Decreasing to increasing, we have a local minimum, okay? And then for the second derivative, what are my numbers that I have to focus on? Where does the concavity change?
Negative 2
Negative 2
and 0.
and 0. So for my second derivative, we're looking at a number line like this. And they give us all this information, okay? It's negative in between, positive on the outsides. All right. Which means, do I have points of inflection anywhere? Where? X equals negative 2 or 0. So I'm going to have some points of inflection here. Okay, now, here's how I start off with this. Now you've got to take all this information and put it together. The first place I'm going to start is with these horizontal tangents. Okay, now, you don't have to draw the little horizontal tangents in, and I put them where I put them. Okay, we don't have an equation. Could I have put this one up here? Sure. Could I have put this one over here? Yeah, right? It doesn't matter exactly where you put them, but you have to have one somewhere, and you just have to pick. Okay, so I'll go back to where I had them, just because those are the ones I picked. Okay? Now, so I have a local max up here. This is a local max. So what I'm thinking is there's something going on like this. And then before I draw anything like that, I got to think about the concavity, because it's supposed to be concave down only from negative 2 to 0. So only in here am I concave down, right? So that's why I have something like that. Everywhere else it's concave up. So it's got to be concave up here. It's got to be concave up here. Actually, that made it seem like it's going down. It's going to be concave up like that. Okay. And here, it can be concave up the whole time. But we got to keep in mind that, does this satisfy, am I increasing? Where am I supposed to be increasing? I'm supposed to be increasing less than -1, so I'm increasing, and then I'm decreasing greater than 1. So it still has to be decreasing. It has to keep going down. Okay, and then on this other side, less than 1, I'm sorry, I said it backwards. It has to be increasing. Increasing. Okay. Which just means the slope of the tangent line has to be positive. Remember what this is saying. The slope of the tangent line has to be positive. The slope of the tangent lines have to be, let's see. Oh yeah, less than -1. Okay, because we're increasing here, decreasing here. All right, so I still need to be increasing from 1 to 0. But in between, I need to keep going down. So it's decreasing here in between -1 and 1. So I have to continue decreasing. I have to keep going down. But the concavity has to change. Okay. So this is what I came up with. So it kept decreasing. Then at that point, it went increasing, and it stays concave up. So it's going concave up forever. Okay. And then over here, it's going to be concave down. You could have lots of different things. Okay. Sorry, it's going to be concave up. It's got to be concave up, and then it also has to be increasing. And when we say increasing, we're talking about from left to right. So from here to here, it's got to be going up. So if I went this way, then it would be decreasing over there. So that would be a problem. Okay. So this is what I came up with. Concave up, the tangent lines are always below it. The graph is always above the tangent lines. The slopes of these are always positive of the tangent lines. Okay, that's one option that you could have. Okay, now I came up with some other ones. If you started in different spots than these two, like I showed you how you could move them. Okay, so I have one that looks like that, still satisfies all of it. Okay, still concave up the whole time, still increasing that whole time, still increasing this whole time, still concave up the whole time, and then I came up with one more. Okay, again, still increasing this time if I chose different spots for them. So there's lots of different possible answers that you could have. But the trick to problems like this is you have to synthesize all of this information and then check it and check it and check it and make sure you're like, okay, do I have all the spots where they should be meeting all those conditions, okay? This is something you're going to need to give yourself a little time to work on because it's not easy.